afternoon. Let me introduce our next speaker. It's Rohil Prasad, and his talk is on low-action holomorphic curves and invariant sets.
Thank you. And is this working? All right. And how does my handwriting look? There's a writing sample right there. OK, great. Well, thank you all for having me here. It's really a privilege to spend a week listening to all these great talks in this beautiful city. So my talk today is joint work, which is, I guess, very much in progress with Dan Christopher Gardner. There's a lot of moving pieces, essentially. So we need to still get those sorted. So I'm going to talk about the problem of detecting non-trivial invariant sets of dynamical systems. This is a very fundamental problem. It's been the subject of lots and lots of work ever since dynamical systems existed. But this work kind of follows a more recent line of thinking, which was proposed, I guess, in an influential survey by Bramham and Hofer, and later in some very exciting recent work by Fish and Hofer, that you should be able to use techniques from symplectic geometry like holomorphic curves and floor theory to detect non-trivial invariant sets of dynamical systems of symplectic origin. So what I'm going to do in this talk today is I'm going to describe a method using specifically low-action holomorphic curves in symplectizations to detect invariant sets and apply them to symplectic dynamical systems of low dimensions. So this means area-preserving diffeomorphisms of smooth surfaces and three-dimensional Rabe flows. Okay. So the talk itself is going to be fairly linear. I'm going to give some background, state the main dynamical results, and then try and get through all the ingredients needed for the proofs of the main dynamical results. Okay. So I'm going to first talk about some classical results for homeomorphisms of the two-sphere. So there's a well-known result by Lecalves and Yacos in '97, which says that if the map phi has a finite number of periodic points, then the diffeomorphism phi is not minimal on the complement. And by not minimal, what I mean is it has a non-dense trajectory. So in other words, if you take the closure of this non-dense trajectory, you get some kind of new invariant set, which is not any one of the finitely many periodic points of phi. And shortly after this, Franks came up with a different proof in 1998 of a slightly stronger statement, which is, so if you have the same hypothesis, that the number of periodic points is finite, then the set of periodic points is not an isolated invariant set. So this is a notion that was introduced by Conley, and roughly what it means, well, what it means to not be an isolated invariant set is that you can find non-trivial compact invariant sets in arbitrary punctured neighborhoods of the set of periodic points. So the Lecalves-Yacos theorem says you can find one, and the fact that, and then the Franks theorem says that you can actually find, all sorts of interesting invariant sets, getting closer and closer to the set of periodic points. Okay. Now, and then later, I believe I don't understand the proof super well, but basically building on the Conley index methods used by Franks, Salazar showed a result for area-preserving homeomorphisms, but without the assumption that the number of periodic points is finite. So let's suppose that phi is area-preserving. Then the following two results are true. So first is that phi is not minimal on S2 minus lambda for any compact invariant set lambda. And the second one is that the closure of the set of periodic points is not an isolated invariant set. Okay. So these are all results about homeomorphisms of S2. Okay. And now another much more recent result, which I should mention, can be thought of basically as a higher dimensional version of the Le Calvez-Yoccoz and Franks theorems. This was mentioned by Victor on Monday. So this is due to Ginsburg-Gorel, 2018. And what this says is if you have a Hamiltonian diffeomorphism, or non-degenerate, Hamiltonian diffeomorphism, and if the number of periodic points is finite, then these results also hold. The way that they stated it is that the periodic points, none of the periodic points are isolated as an invariant set, but you can basically, by using an elementary argument and combined with their methods, get this slightly stronger result. Okay. But, oh really? I didn't know that. Oh, very nice. Okay. Okay. All right. Sounds good. Okay. So now I'll try and talk a little bit about the methods behind each of these results. So, well, very, very, very briefly. So the Le Calvez-Yoccoz result follows as a consequence of a much stronger result, where they compute the Lefschetz index of a fixed point of a plane homeomorphism, assuming that that fixed point is not a source or a sink. So in particular, the way you derive this theorem is you assume for contradiction that it is minimal on the complement of the periodic point set. Then, using the Le Calvez-Yoccoz formula, you get that after iterating sufficiently many times, the sum of the Lefschetz indices of the fixed points is non-positive. But this is a contradiction because S2 has positive Euler characteristic. So that's how you get a contradiction. And then, told from this perspective, the Franks and Salazar results are pretty similar in spirit. But instead of using the standard Lefschetz index, they use the Lefschetz index of the Conley index of the periodic points. And then they do a similar thing. They show that that is non-positive, and then but on the other hand, the Euler characteristic of S2 is positive. Okay. And then the result in this case makes use of the fact that diffeomorphisms of this type are what Victor and Bashak described as gamma rigid. So there's a subsequence of iterates for which the gamma norm goes to 0.
What's the conclusion of the theorem on the right?
Oh, I just didn't want to rewrite these same results, or I should say analogous results. Yeah, I'm being a little loose, I guess, because well, combined with Agor's result, I guess you know that it's n+1, but you know, this is. Oh, the non-degeneracy. Oh, okay. Sure. Okay. So. Yeah. Yeah. You're right. It depends on what you mean by isolated invariant set, I suppose. If you use the definition I have in mind is that you have an isolating neighborhood which strictly contains that set. So by default, this cannot happen if it's the entire thing. Yeah, but yeah, this was actually some kind of personal point of contention. I think I was basically leaving it to the reader to decide that this is only interesting if the closure of the periodic points is not everything. Yeah. Yeah, I mean, yeah. Otherwise, it's not so interesting, anyways. Yeah. Okay. Right. Yeah. So yeah, and then so this result uses the I guess gamma rigidity of maps like this, but I guess as we've seen this week, the gamma rigidity doesn't. The gamma rigidity is known to not hold generically. And in fact, in Agor's talk, Shalukin mentioned this conjecture of Polterovich, which said that gamma rigidity, I guess, never holds for aspherical symplectic manifolds. So the main theorem that I want to discuss is about higher error-preserving diffeomorphisms of higher genus surfaces. So these are aspherical, so Hamiltonian diffeomorphisms on them are probably not gamma rigid. And they also have non-positive Euler characteristic. So the Lefschetz/Conley index methods will not work without additional information. However, using symplectic methods, you can still find some kind of result for higher genus surfaces. So let me fix sigma to be a closed surface and phi to be an area-preserving diffeomorphism. So then, if phi is what we call rational, this is some kind of weak homological restriction. In particular, it includes the Hamiltonian diffeomorphisms. Then we have the following then we have the analog of Salazar's results. So first of all, phi is non-minimal on sigma minus lambda for any compact invariant lambda. And second, the closure of the set of periodic points of phi is not an isolated invariant set. Yeah, I guess just provided it's not the entire thing. Yeah, you're right. A and B follow from one statement, which just says that if you take any compact invariant set which contains all the periodic points, then that's not isolated as an invariant set. Yeah, I'm just writing it this way to align more with the statements of prior results. Okay. And so just a couple of comments on the statement here. So some kind of rationality condition is definitely necessary. So a remark is that there are irrational counterexamples So for the torus, such an example would be an irrational rotation. And for higher genus surfaces, you can have counterexamples given by time one maps of minimal translation flows. And another remark that I want to make is the following corollary, just because these statements are fairly technical. So I want to give some kind of more concrete statement about invariant sets that's a consequence of this. And so a corollary of I believe, of part A is that for a dense set of points z in sigma, the trajectory, which is given by just the set of all iterates of z, is not dense. So in particular, we get that these maps have a variety of non-trivial invariant sets which are kind of spread throughout the manifold. In some sense, maybe this might not be too surprising considering results that you know in the generic case. I mean, you have much stronger results in the generic case. You actually know that periodic points are dense. Yeah. But the point of this is that it's completely non-perturbative. This just holds for any of these rational area preserving maps. Okay. Yeah, that's a very. Yeah, by Salazar's result. Yeah. In fact, Salazar's result is even for homeomorphisms. I'm looking at smooth maps, and I think the case of homeomorphisms is very much open for higher genus surfaces. Okay. All right. All right, and then in addition to this result about area-preserving diffeomorphisms, we have an analogous result for Rabe flows in 3 dimensions. So analogous results hold for for Rabe flows on y c, where y is equal to a closed 3-manifold, and C is a contact structure, and right now we have this technical condition that we require the first Chern class to be torsion. And so this case contains some classical situations like star-shaped hypersurfaces in R4. Okay. So does anybody have any further questions about any of the statements? Okay. So now I'll get into describing the method of proof. As I kind of briefly mentioned, the first piece of this is a method using low-action holomorphic curves to construct invariant sets. So roughly what I'll show is that for, or what?
This last result, you mean that there exists a contact form that it holds?
Oh no, any contact form. Yeah. With that contact structure, yes. Yeah. So the rough way that the arguments go is that using holomorphic curves, you can show that if you have a stable Hamiltonian manifold, which has, in some sense, enough low-action holomorphic curves, then you can extract these types of Le Calvez-Yoccoz type results. And then the second component of it is to show that these classes of systems actually have enough low-action holomorphic curves. And this relies on properties of periodic flow homology and embedded contact homology, respectively. And as an aside, it was kind of really great that Brian gave such a nice and detailed introduction to ECH in his talk before. I was in the audience and I just crossed out a whole page of my lecture notes after that. So thanks. Okay. So let's talk about holomorphic curves. So this part of the discussion is going to be in some reasonable level of generality. I'm going to fix some odd-dimensional closed manifold. And I'm going to fix a pair lambda omega, which form a stable Hamiltonian structure. So this formalism includes both contact manifolds and mapping tori of symplectic diffeomorphisms. Okay. And I'm going to fix the notation that R is equal to the Rabe vector field of this stable Hamiltonian structure.
Can you say a little bit more about the definition of a stable?
I can, yeah. So let's maybe go down here if it's not too invisible. So it's a stable Hamiltonian structure if it has the following properties. So one is that omega is closed. The second property is essentially that omega is maximally non-degenerate. So this means that lambda wedge omega to the n. This is a top dimensional form. We want this to be positive. And then the third property is what's known as the stability condition. And this says that the kernel of omega is contained inside the kernel of d lambda. This is kind of hard to motivate just from writing it down. It turns out that this property guarantees, so let me put it this way. Any Hamiltonian energy level in a symplectic manifold has a fairly natural structure like this. And what this stability condition guarantees is that you can find a transverse vector field, kind of like a Liouville vector field, which after which you can flow the hypersurface along this transverse vector field, and it'll preserve the characteristic foliations in this family. So that's where stability comes from. Like the characteristic foliations are stable under it.
Why lambda is not necessarily the contact number?
No. So as I mentioned, this formalism contains both contact manifolds, and it also contains mapping tori of symplectic diffeomorphisms.
Thank you.
So I'm going to fix some admissible J on R cross Y. And I'm going to give R the coordinate A. And it's admissible if it satisfies the following three properties. First, it's translation invariant. Second, it incorporates the Reb vector field. So J of the real coordinate tangent vector, dA, is equal to the Reb vector field. And then the third one is a little harder to state concisely. It's that J is omega compatible on the kernel of lambda. And so following the original setup by Hofer, we're going to work with holomorphic curves, J holomorphic curves, where J is admissible. All right, so take some J holomorphic map. This. Here, C is a punctured Riemann surface, and U is some proper map, which satisfies the J holomorphic curve equation for our choice of admissible J. And the geometry of this map is controlled by two quantities. The first one is called the action. I call it the action. So this is just equal to the integral of this stable Hamiltonian 2 form over the curve. And you can check that this is always some non-negative number. The second quantity is called the Hofer energy. And I'm going to write this in a slightly non-standard way. So this is the quantity given as follows. I'm going to take the suprema over all regular values t of the projection to R of the following quantity. I'm going to integrate over the level set with respect of the curve with respect to t. So this is the intersection of the curve with the slice t cross y of this one, and I'm going to take the integral of this 1 form lambda. And you can check that this is also non-negative. Okay. And so what's the importance of these two quantities? So the Hofer energy was just So the Hofer energy was discovered by Hofer, and he showed in his classical 1993 paper that when both the action and the Hofer energy are finite, then a holomorphic curve of that form will actually limit off to infinity to periodic orbits. Okay. And the action I want to talk about in a little bit more detail. So when I think about the action, I have the following heuristic in mind, which is that the action gives some kind of control on how close the curve is to the Rib vector field. So it controls the average distance of the tangent planes of U of C to the vertical distribution. So this is the subbundle spanned by dA and the Rib vector field. So in particular, you can show that if you have a curve of zero action, then it's actually contained inside a cylinder over a trajectory of the Rib vector field. Okay. So with this heuristic in mind, we can consider sequences of curves whose action goes to zero. So I'm going to fix a sequence of holomorphic curves U sub k. Such that the action goes to zero. And by this heuristic, we would kind of expect these holomorphic curves to approximate the Rib vector field better and better. And this heuristic can pretty easily be made a reality if these holomorphic curves have bounded Hofer energy. In fact, in this case, you can show that they converge on compact sets to a finite union, to a cylinder over a finite union of Rib orbits. However, if their Hofer energies blow up, then it's a little more complicated. All right, so with this in mind, I'm going to make the following definition. So the limit set, which I'll write as X, is the collection of subsets lambda and Y, which arise as a limit of level sets of this sequence of curves. So there exists a sequence of real numbers S sub k and a subsequence of the resulting level sets. So this is CK intersected with SK cross Y that converge to lambda in the Hausdorff topology. Okay. So you would expect really that since the actions go to zero, these holomorphic curves get closer and closer to the Rib vector field. So these level sets kind of get closer and closer to being trajectories or unions of trajectories of the Rib vector field. So you'd expect that this Hausdorff limit is actually an invariant set. And the main technical theorem that I want to state verifies exactly this, but you need this additional technical assumption that the topology of the curves is bounded. Yes. Okay, so now I'll state a technical result. So suppose you have a sequence U sub k such that the following two properties are satisfied. So 1, their actions go to 0. And 2, the absolute values of the Euler characteristics of the domains are uniformly bounded. Then the limit set satisfies the following properties. So first of all, it's connected with respect to the Hausdorff topology. And second, every set in X is R invariant. Okay. And the third thing, and there's also a kind of third conclusion, which is also pretty useful. Which is that, and also, if we assume that each of these U sub k have finite Hofer energy, then we can show that C, there exists some set lambda in the limit set such that lambda lies inside the closure of the set of periodic orbits. Okay. So just to comment on the statement, A is quite elementary. The proof is identical in spirit to the proof that the omega limit set of, say, a gradient flow line of a Morse function is connected. C is also fairly elementary given prior results, because if each of these holomorphic curves have finite Hofer energy, then kind of very close off to infinity, their level sets are close to periodic orbits. Okay. The real content of the theorem is part B. That's the main non-trivial part, and that's the part that requires the bound on the Euler characteristic there. In fact, it would be really great to remove the bound on the Euler characteristic, because it would actually cut this talk almost in half, or cut off maybe 30% of this talk. Okay, so does anybody have any questions about the statement of this theorem or any of the definitions? Okay. So now I'm going to describe how you use this technical result to deduce these dynamical applications that I mentioned. So here's a definition. So I'll say that Y has enough low action curves if for every z and y there exists a sequence of holomorphic curves U sub k satisfying a bunch of different properties. So the first one is that all of them contain the point 0z. The next two are that they satisfy the hypotheses of this technical theorem. So we want that the actions go to 0 and that the Euler characteristics are bounded. And then the fourth assumption, which I'll make, is that they all have finite Hofer energy for every k. And this is so that I can eventually use this part of the theorem. And just to stress exactly what I mean by this assumption, I'm not assuming that the Hofer energies are uniformly bounded. In this case, the theorem would be known. Or, in this case, you could get a lot more from having enough low action holomorphic curves. So the Hofer energies, I'm just requiring that they're finite, but they might blow up as k goes to infinity. Okay. And so the main technical proposition is that systems with enough low action curves satisfy these Le Calvez-Yacoz type results. So proposition, so suppose Y has enough low action curves. Then for every compact invariant lambda, which I guess is a strict subset of Y, such that all the periodic points are contained in lambda, then we know that lambda is not isolated as an invariant set. Okay. So any compact invariant set containing all the periodic points, one example would be the closure of the union of periodic orbits, is not isolated as an invariant set. And the proof I am just going to draw. Mm-hmm.
So those results are known, they are true
Well, you need the system to have enough low action curves.
Yeah.
So for example, for pseudorotations of CPN, this is true, because the gamma rigidity gives you lots of low action cylinders through any point. Yeah. Yeah. Okay. So let me just kind of draw the proof. So this is our periodic point set, and this is lambda. And and what we know from having enough low action holomorphic curves is that if we pick a point Z, a point constraint Z outside of lambda, then you'll have a sequence of low action curves passing through Z. Then applying this technical theorem, you can show that the limit set of these curves contains some invariant set lambda prime, which contains Z. This drawing is a little inaccurate. Lambda prime might not be disjoint from lambda, but this doesn't matter. Then the point is that you also know that the limit set is connected with respect to the Hausdorff topology. So roughly speaking, there's a family of invariant sets which interpolate between lambda and lambda prime. And this immediately means that lambda cannot be isolated as an invariant set, because you'll have a kind of infinitely many elements of this family which approximate lambda in the Hausdorff topology. Okay, so this is the main input from holomorphic curves. And now I'm going to return to these low-dimensional systems. I'm going to describe why rational area-preserving diffeomorphisms satisfy this technical condition, why they have enough low-action holomorphic curves. So does anybody have any questions before I start erasing everything? Okay. Sorry?
Are you also going to have low-action curves for that?
We can only show it in the torsion case. I would be,
Torsions needed for the Euler's characteristic pattern.
huh?
Torsions because you want an Euler characteristic pattern.
Yeah, we use the J0 index, yeah. Okay, so let's get back to surface diffeomorphisms. So I'm going to fix a diffeomorphism phi of a closed symplectic surface. And I'm going to associate to it a stable Hamiltonian manifold via the mapping torus construction. So the mapping torus, you just take the interval across the surface and you glue the ends together by phi. Okay. And this admits a natural stable Hamiltonian structure, which I'll write as dt omega sub phi. Okay. And just to explain these terms, I'm giving the interval the coordinate t. So you have this exact one-form dt upstairs, and this descends to a closed one-form dt, which I'm also writing as dt downstairs. And then this omega sub phi, in a similar way, just comes from the area form pulled back to this cylinder and then pushed down into the mapping torus. Okay? And it turns out that this is a stable Hamiltonian structure and that the Rabe vector field generates the suspension flow of phi. Okay. So now I'll finally tell you what I mean by a rational area-preserving diffeomorphism. So I'm going to say that phi is rational if this two-form satisfies the following condition. If you normalize it by the area of the surface, then it represents a rational cohomology class. And you can check by explicit computation, for example, that Hamiltonian diffeomorphisms satisfy this property. Okay. And so the main proposition that I want to outline is that the mapping torus is that if phi is rational, then y sub phi has enough low action curves. Okay. So the way that we're going to produce the low action curves is using what's called the UMAP on periodic flow homology. So thankfully, Brian already explained the theory of ECH for contact manifolds, and he explained that ECH had this UMAP structure, which counts ECH index 2 curves with point constraints. There's a cousin of ECH for mapping tori of surface maps called periodic flow homology. And this also has a UMAP, which counts ECH index 2 curves with point constraints. Okay. So I'm not going to give a definition, but I'll just give a technical statement, which is what we get out of known properties of periodic flow homology. So let's fix phi rational. Then for every integer, for every sufficiently large integer d bigger than 1, and any generic point z in the mapping torus, and I'm also going to take j to be sufficiently generic, but I'm just not going to write that down. There exists an integer, m greater than or equal to 1, and a and a holomorphic building C1, C2, all the way through M d minus g plus 1. So it's a holomorphic building in R cross the mapping torus with exactly this many levels. So it's M times d minus g plus 1, where g is the genus of the surface. And this building satisfies a bunch of properties. So the first property is that the top and bottom limits, so these are sets of Rabe orbits, coincide. Or I'll write this as A. All right. And then let me remember what order I wrote these in. Right. Then B is that each of these curves, C sub k, has ECH index 2. So I is equal to the ECH index. Okay. Property C is that the sum over all k of the relative homology classes of these curves. So just as a note, since this building has the same top and bottom limits, if you add up all the relative homology classes of these curves, you get a genuine two-dimensional homology class in the mapping torus. So this is equal to M times the homology class of a fiber. Okay. And then D, what did I write for D? Oh, yeah, of course. D is that the point 0, comma z is contained inside C sub k for every k. Okay. So in the last 7 minutes, I'm going to take some large D, and I'm going to show you by a probabilistic argument that most of these curves have bounded Euler characteristic, and that most of these curves have low action. And this kind of probabilistic argument goes back to work by Hutchings and Taubes and by Cristofaro, Gardner, Hutchings, and Pomerleano, studying 3D Rabe flows with finitely many periodic orbits. And oh, okay. I should also mention the proof of this, or mention the proof of this proposition. I'll be very brief on this. So the proof. So this uses what's known as the U-cycle property of PFH, namely that PFH contains a lot of classes where the U-map essentially returns a homology class to itself. And this property was first introduced by Ettmeyer and Hutchings, and I guess verified for the sphere and the torus, and then later with Dan Boyu Zhang and Dan Pomerleano, we verified it for all surfaces. Okay. All right. So first, I'm going to verify that most of these curves have low action. Okay? Okay, so this is not so bad. I'm going to take the sum of the actions of all the C sub k, and using property C, we notice that this is the same thing as M times the integral over the surface of omega. Then, now what this implies is that since there's about M times D of these holomorphic curves, what this means is, I guess, at most, what this means is that most curves should have action bounded above by, say, m times d to the minus 1/2. Because if there were, if you imagine if all of the curves, or I can even just write d to the minus 1/2. If all of the curves had action bigger than d to the minus 1/2, then their total action would be something like m times d to the 1/2, which is way bigger than this. Okay. And the slightly more complicated part of this is showing that most of these curves have bounded Euler characteristic. Okay, so there's a result due to Hutchings, which bounds the Euler characteristic of a curve in terms of a cousin of the ECH index. So he shows that minus, if C is some holomorphic curve in a symplectization, he shows that minus its Euler characteristic is bounded by what's called the J0 index. And this is equal to the sum of the following three terms. It's the ECH index minus 2C tau of C. This is the relative Chern class, or Chern number. And then minus what I'm going to write as CZ top of C. So this is just some sum of Conley-Zander terms. Okay? Now in our case, so what we're going to do is we're going to look at we're going to try a similar argument to the one for the action. We're going to try and bound the sum of the Euler characteristics of all the C sub k. So this is bounded by the sum of all the J0 indices, which is equal to the sum of the following three terms. So this is the sum of the ECH indices and minus 2 times the sum of the Chern numbers, and then minus the sum of the Conley-Zander term. All right. So I really don't want to erase that. My apologies. I'm going to actually move over here. Okay, so we're going to consider each of these three terms separately. So, all right, so first, using assumption B, we get that each of these ECH indices is 2. So when we sum over all k, we get 2m times d minus g plus 1. Okay? Now, if we use C, we get that the sum of the homology classes of all the C sub k's is just m times a fiber. So we get that the second term evaluates to 2m times C1 times C1 evaluated on sigma. So this is C. And then finally, the Conley-Zander terms all cancel out. And this is just because of the fact that the top and bottom limits coincide. Okay? And we can easily evaluate this. This is just 2 minus 2g. And so we get that this is equal to 2m times d plus g minus 1. Okay? And then what this tells us is that the Euler characteristic of C sub k has to be bounded above by 2 with a positive probability. Or by positive probability, I mean kind of independent of what this large parameter D is. And so using this, you can pick out a low action curve with bounded Euler characteristic, which passes through this point constraint Z. And that's enough to show that surface maps have enough, or rational surface maps have enough low action curves. Okay, so that was a little technical towards the end, but I apologize. That's all I have for today.